Sequential circuits are an integral part of digital systems, allowing for the storage and processing of information over time. Unlike conventional circuits that solely rely on input values to produce an output, sequential circuits introduce the concept of memory and internal states. Sequential circuits are designed to remember and utilize past information, making them capable of performing more complex tasks. They can be broadly classified in two types, which are synchronous and asynchronous. Synchronous sequential circuits are driven by a clock signal, which ensures that the circuit's operation is synchronized and coordinated. The clock signals determines when the inputs are read and the outputs are updated. While the asynchronous sequential circuits, also known as self-timed circuits, do not rely on a clock signal for their operation. Instead, they utilize control signals that depend on the changes in the inputs and the internal states. Both synchronous and asynchronous sequential circuits have their advantages and suitable for different scenarios. The choice between them depends on the specific requirements, constraints, and trade-offs of the given application. This code implements a synchronous sequential circuit. The circuit controls a 7-segment display, which is a common component used to display numerical and alphanumeric characters. The circuit operates synchronously with a clock signal, transitioning through different states and updating the display based on the current state and the counter value.
The module's lid has 3 input or output ports: SIG for the 7-segment display output, DIG for the digit selection output, and clock for the clock input. The circuit consists of several registers: SIG, DIG, display data, count, and state, that store the state and data values. The state register is a 3-bit register that represents the current state of the circuits. It transitions through different states based on the current specified in the state transition logic. The state transition logic is implemented using a case statement. Each state transition specifies the next state to transition to. The digit register is a 4-bit register that determines which digit of the 7-segment display is active. The digit selection logic is also implemented using a case statement. Each state corresponds to a specific digit being enabled, and in the default case, all digits are disabled. The count register is a 37-bit register used as a counter. It increments by 1 on every rising edge of the clock. The display data register is a 4-bit register that restores the data to be displayed on the 7-segment display. The value of display data depends on the value of count. If count is 0, the display data is set based on the upper 4 bits of the count. Otherwise, the display data is set to 4 bits 0000. The 7-segment display logic is implemented using another case statement that maps each value of display data to the appropriate 8-bit value for the corresponding digit or character to be displayed on the 7-segment display. The default case is set to display nothing.
All this code represent a synchronous sequential circuit because it uses a clock signal to control the timing of state transition from data updates. The register holds the state and data values, and their updates are synchronous with the clock. The circuit progresses through different states based on the current state and update the display based on the count value and the current state.
This code can be implemented on a field programmable gate array or FPGA to control a 7-segment display. The FPGA contains programmable logic blocks that can be configured to implement digital circuits. The code describes the sequential circuit behavior and the connections between different components. The clock input serves as the clock signal for the circuit. On each rising edge of the clock, the circuit updates its internal state and outputs. The circuit consists of registers that store the current state, digit selection, display data, and a counter. These registers are implemented using flip-flops within the FPGA. The state transition logic determines how the circuit progresses from one state to another. Each state transition updates the state register. The digit selection logic determines which digit of the 7-segment display is enabled. The dig register controls the digit selection pins of the display. The count register acts as a counter that increments by 1 on each clock cycle. The display data logic sets the value of this dot register based on the counter value. Finally, the 7-segment display logic maps the value of this dot to the appropriate segments to display the desired digit or character. The seg register holds the value to be outputted to the 7-segment display. By programming the FPGA with this code, the circuit can control the 7-segment display by sequentially enabling different digits and setting the appropriate segments to display the desired information. Overall, the FPGA is programmed to implement the sequential circuit described in the code, allowing it to control the 7-segment display based on the internal state counter value of synchronized with the clock signal.